video, we're going to go into more depth on isomers. So when we look at isomers, this is a great chart to start with. It classifies isomers into two main categories. There's something called constitutional isomers or structural isomers, and then also a type of isomers called stereoisomers or also spatial isomers. And within the stereoisomers, you can have what's called diastereomers, which are cis-trans isomers, and then you can also have enantiomers. And so a really good learning tool in really any course, but especially the sciences, is to make these little charts and graphics to help you put terms together. And it really consolidates and summarizes information. It's a great way to take a lot of note and really put it into one place to show that you're understanding the relationship between things. So we're going to start off with the constitutional isomers or structural isomers. And these are isomers that have the same molecular formula, but their atoms are going to be bonded in a different sequence. So it's the exact same molecular formula, but atoms bonded in a different order. So for example, here we have in this molecule, the formula is C3. I'm just counting the number of C's. H, we have 1, 2, 3, 4, 5, 6, 7 H's, and then F. Over here, if you count everything, you'll see the same idea. We have C3, H7, and then F. So same formula, but notice here the F is on the middle carbon, and here the F is on the carbon at the end. And so even though they have the same formula, they're different compounds. And one way to sort of prove it is to name it based on our naming rules. So here we can see we have 1-fluoropropane. You don't have to put the 1 because it's implied there. And here you can see you have 2-fluoropropane. Same formula, just different bonding sequence. And so that different bonding sequence will lead to different properties as well. So you have different physical properties like boiling points, and that's really because they have different shapes and different forces that take place in different areas, and that's what leads to different physical properties. So we'll take a look at how to draw isomers given a formula. And here's a great example you can do. It takes practice. You do have to try this out and develop strategies as you go. There's only really one way to get good at this, is practicing. So we have draw all the constitutional isomers for C4H8. In other words, draw all the structural isomers. Draw all the different ways you can represent C4H8 specifically, and it has to abide by that formula. So there's a couple things I do. First of all, I look at this formula and I try to think about what type of substance or molecule or organic compound this is. And this looks like the general formula CnH2n. And so from that, I know that this is likely an alkene. There's probably a double bond in there. It could also be, if you think about it, a cycloalkane, because cycloalkanes have that same general formula. But it wouldn't be an alkane, an alkyne, because they have different formulas. An alkane would be, CnH2n plus 2. So in other words, if this was an alkane, you'd see C4H10, and then you could do your isomers of that. But it's not that situation there. It's really this and this. So we need to see how many different alkenes and cycloalkanes we can make with C4H8. A good first strategy is to just make the longest chain possible from these atoms. So I'll put 4 carbons. 1, 2, 3, 4. I'll put in a double bond, let's say over here, carbon number 1. And then I'll go and I'll just put in my other bond. So here I have, this would be H2, this would be H2, and then CH3. So what did I draw here? I drew butene. And it's important to write the names, and you'll see why in a little bit. So let's see what else we could do. Well, we could draw a long chain again. And we could do 4 carbons. But my next strategy is going to be, can I move the double bond to make something different? So I'll put the double bond here. And what that does is it moves my H's around, right? It's still the same C4H8, but my H's will be in different carbons. So I'll have the C3 over here, the CH here, CH here, and then CH3 there. So let's just double check to make sure that's correct. 8 H's and yep, 8 H's. Okay, so now what I'm going to do is I'm going to write the name out. So notice this is on carbon number 2 now. Whoops, I shouldn't underline that because it looks like a triple bond. And this is bute to ene. So I'm going to continue this approach. I'm going to try now to maybe move the double bond one more time. And so this is what students will often do. They'll do this. They'll move the double bond right over here, and they'll get this. And so they'll say, oh, it's a different molecule. Like there's a different position for the double bond. That makes sense. I have another isomer here. And yes, it's the same formula, but what I want you to notice is that if you name it, this is carbon number 1 now. This is simply butene, just flipped. It's the same molecule as one above, so this doesn't count, so be careful. It's very easy to think this is a different molecule than 1 and 2 because you have double bond in different position, but it's the same thing when you name it. It's still butene, we just flipped it around. So you just have to be very, very careful when you're doing this so that you don't jump to conclusions and think you actually made another isomer there. It looks like I've made the most 4 carbon chain molecules. So now what I'm going to try to do, my next step is let's try to make some branches maybe. Let's try to make some branched molecules. So maybe I'll make a 3 carbon chain with a double bond and then put a branch somewhere. So let's do a 3 carbon chain. We'll put a double bond here. And then we'll take one of the carbons and put it, let's say, over here. And so this is CH2, this is CH3, and this is CH3. And so I have a 3 carbon chain with a double bond and then a side chain. And this is actually a different molecule from 1, 2, and 3. This is, let's see, this is 1, so it's propene, and it's 2-methyl. So 2-methyl propene. And so here we have a different molecule from 1, 2, and 3. It is an isomer. It has the same molecular formula, C4H8. You can count them. There's 1 carbon, 2 carbons, 3 carbons, 4, then 3 hydrogens plus 3 hydrogens, that's 6, plus 2, that's 8. So also has C4H8. So it's good to verify that. So C4H8. These are also C4H8 if you count them. And they are constitutional isomers because we did change the positions of atoms as we created these. And don't be fooled though. There's different ways to draw this. I'm not going to redraw every single way, but be very, very careful when you're taking this approach because, for example, let's say you do this. Some students might draw this differently. They'll connect this in different ways. They'll say, well, you know what? Let me try this. Let me do this double bond, CH3, CH3, CH2 here, and they'll say, oh, this is different. This is a different molecule because it looks a little bit different, but it's still the same molecule, just kind of rotated around. If you count everything and name it, you'll notice that this is the longest chain, and it's still 2-methyl propene if you name it. So do not count this as an extra one. This is not an extra isomer. This is the same isomer as the third one we drew in orange, but just drawn in a different way. It's the same thing. It's like if I took a pencil and I rotated it in front of you and you said, whoa, it's a different pencil. No, it's the same one. I just rotated it around. It's the same thing. So be careful. They have to be distinct molecules to be considered isomers of each other. And I think this is the shortest chain I can make with branching. So I think now that strategy is over. At this point, it looks like we've got all the alkenes covered. Next, we're going to try to make some cycloalkanes. So let's make the longest chain cycloalkane we can think of with 4 carbons. And that's simply just a cyclobutane. So CH2, H2, 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 like this, like this, like this, like this. and we can call this cyclobutane. And it's C4H8. I think we could do one more. We can try one more. Let me erase this one. That's a non-isomer. Or that's not considered an extra isomer, I should say. Let's make another cycloalkane, but let's make a shorter chain. Can we do a 3-carbon chain? I think so. Let's do a 3-carbon chain like this. And then we'll put another carbon connected to one of the carbons here as a substituent. So CH3 here. This is CH, H2, H2. This is C4, H8. And this is simply methyl cyclopropane. And so what we've done is we started making the longest chain with a double bond first. Then we tried to move the double bond and see if we could make a different molecule, but it's still an isomer because it had the same formula, just different bonding arrangement. And we did that for isomer number 2. For isomer number 3, we said, okay, let's make a shorter chain now because we ran out of the longer chain stuff that we could make. We had redundancies that started to happen. We didn't want to count those. So we said, let's make a 3-carbon chain with a double bond in it, and we got 2-methylpropene. And that's the shortest one we can make. If we move the double bond anymore, we're still going to get the same molecule over and over and over again, 2-methylpropene. It's not extra isomers, just the same molecule drawn in different views. So we're done with the 3-carbon linear chain that's branched, and I think that made us done with alkenes. So we said, let's go and try to make some cycloalkanes, and we take the same approach. We try to make it essentially so that we get the longest cycloalkane we can think of, and we got this cyclobutane over here. Then we made a bit of a shorter one, and we got the methyl cyclopropane, and that's the shortest you can get. And some students might say, why couldn't we have taken this and put on a different carbon? Well, you could have, but if you name it, it would have been the same molecule, methyl cyclopropane. So you're not making other isomers, you're just making the same molecule in a rotation sort of way. And that's essentially it. So there we had an example of making, drawing all the constitutional isomers for a molecule. You can imagine that as you increase the number of carbons and number of atoms, you're going to have more and more and more of them. So here we only had 4 carbons, and we had 5 constitutional isomers. Imagine how many you'd have if you have 5 carbons or 6 carbons or 7 carbons or 8 carbons or 20 carbons. So the more atoms you have, the more ways you can connect them together. It's like the more Lego pieces you have, the more ways you can connect the Lego pieces together, the more variations you can have of a structure that you're building from the same number of Lego pieces. So more Lego pieces gives you more diversity. And that's the really cool thing about organic chemistry is a lot of these carbon-based compounds, the larger and larger they get, you can make sort of different molecules with different properties using the same subset of atoms. So simply using some carbon and hydrogen, I made over here 5 different molecules from this small subset over here. So it takes practice, but with practice you will get it. Another one you can try out, we'll take it up in another video. Try to make all the constitutional isomers for C4, or let's do C5. Whoops. We don't want to print right now. Try to make the constitutional isomers for C5H12. So you can try that, and in another video, you can check your work.